Okay, so this particular lecture is going to be on some important questions on metric spaces for BSc purpose. We are going to discuss some few examples of questionings for metric spaces which are relatively important. Okay, so give me some time. Okay, so let us see a few questions regarding metric spaces. So let's say we start with our question number 1. Okay, I am not going in any serial order in this particular lecture. We are gonna just choose some particular questions. I have a list of those and we're gonna study those. Okay, so one particular question which seems to be quite important is that, see this question. The question is, let A be a subset, let A be a subset of a metric space XD. Define fx equals to d of xa, which is basically the infimum of all possible distances from an arbitrary point x to points in A. Okay, for all A belongs to A, x belongs to x. Clear? Clear? Okay. So we have to prove that fx is a uniformly continuous function. Fx is a uniformly continuous function. Okay, so what do we mean by uniform continuity? So I guess you people know what continuity in real analysis means. Okay, so I'm just giving you a brief example. So suppose you have a function, let's say you have a function from x dx to y dy. So we say f is uniformly continuous on x if and only if for all epsilon greater than 0 there exists a delta greater than 0 such that whenever distance between x and y is less than delta, distance between fx and fy is less than epsilon, where delta is dependent only on epsilon. Okay, in case of continuity, this delta value often gets dependent on the point of continuity. Okay, on the point on which you are trying to prove the function to be continuous. But for uniform continuity, the delta will be only dependent on epsilon. It won't be specific to any point on the metric space. Okay, that is the difference between a continuous function and a uniformly continuous function. That's why all uniformly continuous functions are continuous, but the converse is not true. For example, fx is equals to x square is continuous but not uniformly continuous. Okay, yeah, so we have to prove that this function is uniformly continuous. So let's see. Okay, so suppose we take 2 points x and z, okay, let x and z belongs to the metric space X, capital X, rather let's say capital X, okay, xz belongs to capital X. So for all small a belonging to this set capital A, so for all small a belonging to this set capital A, by triangle inequality, we have d of x a is less than equals to d of x z plus d of z a. Clear? Now moving on to the next page. Now we can apply infimum on both the sides. So infimum over all small a belonging to capital A, d of x small a is less than equals to d of x z, because there are no such points which belong to capital A, plus infimum over small a belonging to capital A, d of z a. So from here we can say infimum over small a belonging to capital A, d of x a, minus infimum small a belonging to capital A, d of z a is less than equals to d of x z. So the left hand side can be written as d of x capital A minus d of z capital A, which is less than equals to d of x z, right? Now what is d of x a? So it is basically fx and this is basically fz. So this is less than equals to d of x z. Okay. Okay. now in this particular statement, that is that I just marked in one interchanging x and z will imply, so what we do is that we just interchange x and z. We have z here, we start with d of z a is less than equals to d of zx plus d of x a. Okay, from there we apply infimum on both the sides, and eventually following the same steps, just with interchange positions of x and z, we have d of z a minus d of x a is less than equals to d of zx, and d of zx is equals to d of xz, right? This is a property of the metric defined on some set. So from, suppose this is, so from here we can say fz minus fx is less than equals to d of xz. So let this be 2 and let this be 3. Moving on to the next page. So this, so basically from 2 and 3 we have modulus of fx minus fz is less than equals to d of xz, right? So now see, now in the definition, so in the definition of uniform continuity, taking delta equals to epsilon proves the statement, right? Because if you take, I'm just writing it here, if you take, let delta be equals to epsilon, therefore for all epsilon greater than 0 there exists a delta greater than 0, such that whenever d of x and z is less than delta, implies, see, mod of fx minus fz is less than d of xz, so this implies mod of fx minus fz is less than delta, and delta is taken to be equal to epsilon, and we can obviously see that delta is not dependent on any of specific points. So this implies f is uniformly continuous. One thing to be noted here, that this function, though not specifically written in the question, is real valued function. Okay, this function f is real valued function, is a real valued function. Okay, so is this question clear? Is this question clear? Okay, so while doing this question, I just mentioned a thing that fx is equals to x square is not uniformly continuous, right? So let us see the proof of that also. That is also a very important example proving that continuous functions are not always uniformly continuous. So question, show that fx equals to x square where f runs from R to R, is not uniformly continuous, okay. See, so we are gonna use a specific approach to this. Let us see this. Okay, so what we do is that we use contradiction method here. Okay, so let if possible fx equals to x square be uniformly continuous, now that implies for all epsilon greater than 0 there exists a delta greater than 0 such that whenever mod of x minus y is less than equals to delta, mod of fx minus fy is less than equals to epsilon. Okay, rather less than, we use strict inequality in this particular definition. Okay, so we do it. Okay, so and to prove this statement, what we take some specific values of x and y to show that a contradiction appears. Okay, so what we do, we take x, let x equals to n, where n belongs to natural numbers, and we take y to be n plus 1 upon n, small n belongs to natural numbers. So what is x minus y? So x minus y is basically n minus 1 upon n, which is equals to mod of 1 upon n. And see, 1 upon n can be made arbitrarily small. 1 upon n can be made arbitrarily small for sufficiently large values of n. So we have 1 upon n less than delta for sufficiently large n. Okay, but for that specific for that sufficiently large n, we need to show that the epsilon, the value of epsilon, or the inequality for the epsilon, the inequality for the image will not hold here. Okay, so what is fx minus fy in this case? So fx minus fy in this case is n square minus 1 upon n square minus 2. Okay, so these two gets cancelled. So this is basically 2 plus 1 upon n square. And see, which is always greater than equal to 2, right, for sufficiently large values of n, right, for sufficiently large values of n, So for epsilon to be half, which is greater than 0, mod of fx minus fy will not be less than epsilon, right, since it is greater than equal to 2, which implies a contradiction, because we had initially assumed that f is an uniformly continuous function, so it must have been less than epsilon, which is not actually happening. So which implies f is not uniformly continuous. Okay, is this part clear? Okay. Okay, let us take the next concept. This concept is related to a very important concept regarding metric spaces, which is called the equivalent matrix. Okay, we are doing that. So the question is saying define equivalent matrix, give examples of two equivalent matrix show that D1 and D2 defined on C01 are not equivalent when D1 of Fg is defined as the supremum of Fx minus Gx such that x belongs to the closed interval 0 1, and D2 Fg is equals to the integral 0 to 1 mod of Fx minus Gx such that x belongs to 0 1. Okay, let us do this particular problem. Now, what are equivalent matrix? So, basically D1 and D2 defined on some space X are equivalent if and only if for all sequences xn in X, D1 of xn x tends to 0 implies, rather equivalent statement, D2 of xn x tends to 0, okay, as n tends to infinity. We can basically say this statement like this, that for all sequences xn converges to some x with respect to D1 is equivalently related to D2, rather for all sequences xn in X, xn converges to x with respect to D1 implies xn converges to x with respect to D2 and converse. Okay. Some examples of equivalent metric spaces include some metric spaces related to real numbers. Examples are D1 xy, which is summation I equals to 1 to n mod of xi minus yi, and d infinity of xi, which is supremum, rather maximum, let us say, because we will be taking an n dimensional real number space, maximum of xi minus yi for all xi yi belonging to R. Okay, these two are metric spaces. These metrics are related with Rn. Okay, Rn d1 and Rn d infinity. Whenever a metric space has equivalent matrix, then we say that both the spaces are equivalent metric spaces. Okay. Okay. Now, what we need to prove is this particular thing, that these two metrics are not equivalent. C01 is the space of all continuous real valued function on 0 1. Okay. Writing it here, C01 is the set of all real valued function on 0 1 such that f is continuous. Okay. Okay. Let us move on to the proof. So, what we do is that we take a sequence, and we say that we will show that it converges with respect to one of the metrics, but not with respect to the other. So, let f n x to be x to the power n and g and x to be the 0 sequence, let's say. Okay. So what is let it be gx only. Okay, constant sequence, gx is equals to 0. That's better, because we will be showing that this will converge to this as x belongs to 0 1. Okay, it converges to this point, xn converges to this point when x belongs to 0 1, right? So that's not a sequence, obviously. This is a sequence. So what is d2 of fg, rather fng, let's say? It is integration 0 to 1 x to the power n minus 0. It is not obvious to write. So this is 1 over n plus 1, which obviously tends to 0 as n tends to infinity, right? Right. Okay. Now what is d1 fg? So it is the supremum of x to the power n minus 0, x belongs to 0 1, and it is obvious from this definition that this value is 1, which does not tends to 0 at all, as n tends to infinity. So this implies d1 and d2 are not equivalent. d1 and d2 are not equivalent. Is this concept clear? Okay. Let us see the next question. Let us see the next question. Okay. Do you people know what is a homeomorphism? Homeomorphism is a specific function from one metric space to other, which is bijective, continuous, and the inverse is also continuous. Okay. So question comes like this: show that the function f from R to minus 1 1 defined by fx is equals to x upon 1 plus mod x is a homeomorphism. Also show that it's uniformly continuous. Now this question is very easy, so I will just give you a few hints to solve this problem on your own. Quite easy problem. See, fx can be written like this, right? X upon 1 minus x when x is less than 0, x when x is equals to 0, and x upon 1 plus x when x is greater than 0. Now if you choose these functions piecewise in the given interval, you will easily be able to find the inverse function, which comes out to be x upon 1 plus x when x is less than 0, x when x equals to 0, and x upon 1 minus x when x is greater than 0. Also x, 1 minus x, 1 plus x are individually uniformly continuous functions. You can prove it with very easy steps. Proving this is very easy. You will just need to go by the definition of uniform continuity, which also implies continuous. Okay, which also implies continuous. So this means x upon 1 minus x, x upon 1 plus x, and x are continuous. So what we can say? So this is a continuous function, this is a continuous function, this is a continuous function. So fx is a continuous function, its inverse exists. The existence of the inverse is quite easily evident from the domain and range given to us. Okay. And also this is a continuous function, this is continuous, and this is a continuous function. So fx is continuous, its inverse exists, so it's bijective, and the inverse function is also continuous because it consists of the same set of functions as in the original function. So this implies that f is a homeomorphism. Okay, fx is a homeomorphism, and we have automatically proved the uniform continuous also. because they are x 1 minus x and 1 plus x, they are individually uniformly continuous. So x upon 1 minus x is also a uniformly continuous function. Is it clear? Is it clear? Okay. Let us check a few counter example related problems. For example, the question is that, okay, is the image of a complete metric space under homeomorphism complete? Is it so that the image of a complete metric space under homeomorphism is complete? See, suppose we take a function f from x to y such that x is basically the set of all natural numbers. Okay, x is basically the set of all natural numbers, and y is set of all numbers 1 upon n such that n belongs to natural numbers. Okay, now x is Cauchy, sorry, my bad, x is complete, not Cauchy, x is complete. Okay, it is pretty evident if you take, no, acha, okay, what is completeness? I am writing it here. What is completeness? See, there are two types of sequences specifically. One we call convergent sequences, one we call Cauchy sequences. Okay, what are convergent sequences? So if for some sequence xn, for all epsilon greater than 0, there exists some n naught in natural numbers such that whenever n is greater than n naught, the distance between xn and x is less than epsilon. This implies xn is a sequence which converges to x, and xn is said to be a Cauchy sequence. Xn is said to be a Cauchy sequence if for all epsilon greater than 0 there exists n naught in natural numbers such that whenever m and n are greater than n naught, the distance between xm and xn is less than epsilon. Okay, so this is a Cauchy sequence, this is a convergent sequence. Now, every convergent sequence is a Cauchy sequence, but the converse is not always true. If the converse is true, then we say that the metric space is a complete metric space. Like real metric space is a complete metric space. Whenever the converse is true, that is whenever in a metric space every Cauchy sequence is a convergent sequence, we say that the metric space is a complete metric space. Okay, so now see, in this case x is a complete metric space. You can verify it on your own, that is very easy. Now see, in case of y, the sequence 1 upon n, we take a sequence from y, the sequence tends to 0, but 0 does not belong to y, which implies the sequence 1 upon n from y is not convergent, but it's obviously a Cauchy sequence. 1 upon n is obviously a Cauchy sequence. Okay, it's always a Cauchy sequence. So that's why, now see, y is this mapping, we have taken this mapping fx is equals to 1 over x. Okay, so the image of x under a homeomorphism mapping is not complete. Okay, so 1 over n is a Cauchy sequence, it is not a convergent sequence, that means y is not complete. X is complete, y is the homeomorphic mapping of x, so the statement is false. Is it clear? 1 upon x is a homeomorphic mapping always. Okay, so I'm ending this lecture here. The next lecture we will be studying some more questions related to metric spaces.